not only was that an astounding shock to the entire scientific worldview, but it has led to innumerable scientific advances that we're all taking advantage of at the very moment. I mean, many of you are now listening to simultaneous translations, and in order to do that, you have little objects in your ear, and the only reason those objects are able to fit in your ear is because of ultra-miniaturization technology due to transistors, and transistors are essentially quantum devices. That is to say, they're devices that take advantage of quantum effects. And even though we take this utterly for granted now, and probably nobody, even somebody who is familiar with the physics of these devices, gives it a moment's thought, it would not be possible for transistors to operate the way they do if it were not for this very phenomenon that I described earlier this morning. Now, we don't normally go around thinking this way. We don't normally go around thinking that the earphones in our ears point to a reality beyond the physical world. But if you will, that's simply because of a failure of our imagination, or because we don't meditate deeply enough about the nature of the physical world, or because we happen not to know that fact. For most of us, it's because we happen not to know that fact. But even for people who do know that fact, oftentimes they just don't meditate about it deeply enough. One can be looking at the equations of quantum mechanics on a blackboard, I've seen this happen many, many times, and be staring at evidence that the physical world is being influenced by something outside the physical world, which should make the hair on the back of one's neck stand up, if you're a sensitive soul. But most people who study quantum mechanics don't react that way. They simply move on to the next problem and crank out the mathematics without stopping for a moment to wonder at the miracle of creation. Because it is miraculous, and it is, as it were, to somebody who understands this, a hidden sign written in the very language of matter itself that something stands outside of matter. It's possible to induce a state of indifference to this fact, but I think that's the wrong reaction. Aviv?
השאלה השנייה, a lot of modern physicists still think that there was a Big Bang. What do they think about the Big Bang? How do they relate it to quantum physics or to physics in general?
Okay. Now, theories of cosmology come and go. So what I tell you now could easily be out of date a few years from now. However, the majority of cosmologists do still believe that there was a Big Bang, meaning, and here too my language is going to be not quite correct because, again, as I mentioned this morning, we now understand that the nature of reality is such that it cannot be visualized. And that was a statement that was made back in the 1700s by a famous Kabbalist, Moshe Chaim Luzzatto. In any event, be that as it may, doing the best I can using language, the implication of the Big Bang is that at some point in the remote past, all of the physical matter of the universe, and there's a lot of it, was compressed into a tiny, tiny point, infinitesimal in size. But the most important concept is not so much that it was infinitesimal in size, as far as its relationship to quantum mechanics goes, but simply that it was so small that the entire universe, the entire structure of the universe was itself subject to the kind of quantum effects that any single quantum particle would be subject to. And that means that this idea of the entire universe unfolding in a completely mechanical fashion, like a giant game of billboards, or the toy train set, or a watch that's been wound up and now can unwind in only one possible way, is completely false. Some of you may have seen seen maps of the so-called background cosmic radiation. It usually looks something like a picture of an oval, and then it has little scattered. Usually it's white on a blue background instead of blue on a white background. But it looks something like this, and it just shows. I won't bother trying to draw the whole thing, but it shows some kind of distribution of matter. And the commentary will say, well, this is what the universe, this is what the sky looks like. And it shows the distribution of matter so many billions of years ago because we're looking at the cosmic background radiation, and it has a variable density. And the point of this is that the specific variation in density is something that emerged one out of a trillion different possibilities. But the particular one that emerged at the moment of creation occurred not because of some mechanical process, but because of, a modern cosmologist would say, because of the quantum indeterminacy that was present when this gigantic universe, now 30 trillion light years in size, was smaller than the smallest possible atom. It was just a tiny, tiny point. Now, what determined the exact arrangement that we see is not anything in that universe, but something outside of it altogether. So, yes, most modern cosmologists still accept some version of this. There are variations on it.
Another question regarding multiple possibilities. In the film, What the Bleep Do We Know, and in other places, there are some scientists who say that there is an option of multiple possibilities even without an observant. If it's so who is the one to say that it's multiple possibilities?
Okay. So first of all, I think in the film actually tends to say that it is the observer that is critical to multiple possibilities becoming one actuality. And really, it's I, in my comments this morning, who said, that's not really exactly right. They got that a little bit wrong, that it doesn't really require an observer. All it requires is an interaction. One bit of matter, a wave function, which carries all these possibilities, interacting with a bit of matter. It could just be a single stray photon, and that will cause the multiple possibilities to collapse into one. So the question here is, in a sense, a philosophical question. Since it's a human being who's constructed quantum theory and is talking about multiple possibilities, if there were no human beings to construct quantum theory and concoct all these notions, who's to say there actually are such things in the first place? And I have to admit that to such questions, there is no answer. In other words, it's a little bit like the question, is there really any universe at all if there aren't human beings around to construct theories of the universe existing? And I don't think I will go into it any more deeply than that, except to point out that there was a previous theory, which also required human beings, which didn't talk about multiple possibilities. It only spoke about one possibility, which was the actuality. And those two theories competed against one another, and the evidence turned out to be in favor of the multiple possibilities. The only thing that quantum mechanics talks about is the appearance out of the multiple possibility of one actuality. And the appearance of the one actuality does not require a human observer to happen. A stray photon can come along and suddenly provoke the actuality. So this is a precise technical point that doesn't require going deeper into the philosophical questions of if a tree falls in the forest and there's no one here, no one there to hear it, is there actually a tree?
Another question that we got from a few different people, they're saying that in many different times in the history, science thought that they go to the boundary of science. So who says that we're reaching the boundary of science now? Maybe tomorrow we'll discover something else. And from your point of view, where do you think the science is going from today on?
This is a good and important question. And it's a subtle one. Because it is always true that a theory can be wrong. So quantum mechanics is merely a theory, and it could certainly end up being mistaken. And there are plenty of scientists out there who have considered quantum theory to be wrong. And there are some scientists out there today who are searching for alternatives to quantum mechanics, or I can't even call it variations on it, fundamentally different versions of quantum mechanics. Such a thing might come along, and were it to come along and fundamentally replace quantum mechanics, then of course everything that I told you this morning would turn out not to be accurate. So that's always possible in science. But there's a subtle distinction. If you think about theories like Einstein's theory of relativity, which, for example, shows that if you speed up a ruler or a yardstick, you have a yardstick traveling along through space, and you make it go very, very fast, it will start shrinking. And you have Newtonian theory, Newton's theory, that says it doesn't matter how fast you speed that yardstick up, it's never going to shrink. Those are two competing theories. And one might think at first that Newton's theory is completely wrong and Einstein's theory is correct. In a simple way of speaking, that's true, but really it's not exactly true. A better way of describing the truth of the matter is that, I'll use technical language at first and then I'll explain what I mean, is that Newton's description is a limiting case of Einstein's theory, meaning for most circumstances that we're familiar with, rulers and yardsticks never ever go anywhere near fast enough so that we see them shrink. So Newton's case is true for the most part. Einstein's view is generally correct. It's not true only under the limited circumstance that we're talking about very slowly moving objects. It's generally true. And in fact, if you speed up yardsticks and rulers fast enough, you will discover that they shrink. Well, quantum mechanics says something very particular. If you come up with any theory for which the quantum mechanical description of reality as we know it now is a limiting case, then everything I said this morning is true. In order for it not to be true, you have to discover that it is completely and fundamentally wrong. That is a possibility. It's always a possibility, but quantum theory has proven itself to be the most successful scientific theory in the history of science. It has been subjected to the most rigorous testing of any theory. It's been subjected to the most outrageous demands. In fact, Einstein himself in the 1930s, before the 1930s, he was so offended by the implications of quantum theory that he couldn't believe that it was true. And he spent years and years and years coming up with an extremely clever idea, namely a particular kind of experiment. And he wrote in a paper in the early 1930s, he came up with this idea that basically said, if quantum mechanics is true, then the following must also be true. And he described a phenomenon which is now known as entanglement, where two objects can be, quote, entangled, and they can be separated as far as 2 galaxies apart. And you do something to one object, and the other object will instantaneously have an association in its state to the first one. You notice I didn't say one object caused the other object. I used the somewhat awkward phrase, has an association. That's in order to be very precise about my meaning. No causal transaction occurred. And the implication was that these objects that were widely separated, they could be galaxies apart, are for all intents and purposes one linked entity. Not one particle, but a linked entity. And as a result, reality could not be thought of as local or localized. Reality had to be thought of as, in some sense, potentially non-local. And in the 1930s, this proposition was understood to be so completely and utterly ridiculous, so contrary to logic and common sense, that it was treated as a logical disproof of quantum mechanics. Until, in the 1980s, an experiment was done to demonstrate that this phenomenon actually existed, and that quantum mechanics was correct, reality is non-local, and Einstein was wrong. So, quantum mechanics has passed so many of the most rigorous and outstanding tests that it is extremely unlikely that it will either be completely overturned, it could happen, or that it will prove to be simply a limiting case of some other theory. And if it does prove to be a limiting case of some other theory, in any event, the principle of non-locality will end up holding regardless, in which case everything I said this morning will remain true.
The next question, is there a scientific proof that there is something, no matter what this something is, that operates the matter, that there is something behind the matter that operates it?
Well, in a sense, quantum mechanics is the closest thing to a proof that there is something outside of matter having an effect on matter. Now, when I use the phrase has an effect on matter, a rigorous philosopher or a rigorous physicist could criticize me for my language, because the phrase has an effect is already using language that should be restricted to physical interactions. And when a wave function that has multiple states contained within it changes to a single state and a bit of reality manifests itself, it is not appropriate to say a cause and effect chain of events has transpired. So my language is being loose there, and the looseness reflects the fact that we don't really have language to describe this accurately. However, the closest thing to what this question asks is present in this phenomenon of there being nothing in the physical world which causes the multiple possibilities within a wave function to collapse into one of those, and choosing which one of those it collapses into. That choice appears to us in our world to be absolutely random. And so it's as if there is some choosing entity or device, I'm deliberately using neutral language here, that stands outside of the universe and makes the choice.
Another question more about the field of science. From searching and finding out that there's a lot of questions without answers, are there in the world of science any doubts about how the world was created?
So there's actually two questions contained in there. One question is, what are the scientific theories about the nature of creation? But the other subtler question, it has to do with the psychology of scientists. And do scientists have doubts about their scientific theories? Well, I would say the greatest and most open-minded scientists are always in doubt and should always be in doubt. Science is a technique at its best. Science is a technique for channeling and using doubt. It should be an instrument of intellectual modesty and humility. If you will, with very little exaggeration, because of the application of statistics in science, you can describe science as the quantification of humility in intellectual pursuits. But the reality, of course, is often just the opposite. And very frequently, we scientists are in a state of great certainty about our hypotheses rather than just the opposite. So the reality is that most scientists are wedded irrationally to the conviction that the creation is a purely mechanical, inanimate, dead entity that came into existence mysteriously but for no purpose whatsoever. And that is, in a sense, an article of religious faith. I mean, you might call it an article of anti-religious faith, but in any event, it is an article of faith. There is not a shred of evidence for it. Neither is there a shred of evidence against it. There is simply no evidence to address such questions within the physical universe. Nonetheless, scientists like human beings, scientists are human beings, scientists as human beings adopt very, very strong attitudes about these things and tend, in the aggregate, statistically, to be fiercely atheistic in their convictions about the nature of the creation.
I think three personal questions that people asked. First, as you said, you were a psychiatrist and then you started researching into quantum physics. What brought you from psychiatry to quantum physics? Is there anything common between them? What were you looking for? The second question is, you as a researcher, as a scientist, what is your dream in the field of research? And the third question, I think, is hiding behind maybe the two of them. Why are you interested in Kabbalah?
Many people ask me the question about, why did I go from psychiatry to physics, and I think are hoping for or looking for a deeper answer than I can give, although maybe the answer that I'm going to give is a deep one. But really it's a very simple and personal one, not a heroic one. When I was very young, I really was primarily interested in physics. I had the great good fortune of having Richard Feynman as a mentor, but I didn't appreciate who he was at the time, nor did I appreciate my good fortune. And I was basically scared of physics and scared of the hard work and the intellectual competition, and so I ran away from it. So basically I was just a troubled kid with a weak character, and went into psychiatry instead. I think I became a decent psychiatrist in spite of my weak character. In any case, I worked on my character, and after a number of years, realized that I had a dream ever since I was a child to be a physicist. And so I guess it was a race between completing the course in physics and total mental deterioration. And so later on in life, I went back and became a physicist because I realized that's what I really wanted to do. And it's as simple as that. Had I been more courageous when I was a child, I would have gone into psychiatry directly. As far as what I'm really interested in, ever since I was young, I always had this intuition that the mysteries of the physical world hid deeper mysteries. And so my studies of quantum physics really, for decades, I have had an intuition, even before I understood quantum mechanics explicitly. I understood that there must have been an appropriate and not superficial, not flaky way of penetrating into the mysteries of quantum mechanics that would point, in fact, towards the spiritual world. I've always had an intuitive attraction towards Kabbalistic teachings. They just struck me intuitively as correct whenever I came across the genuine forms of them. And in terms of my studies in physics proper, I happen to be involved in studies of so-called complex systems, which apply to a wide variety of things. Fundamental quantum theory is something that I enjoy. Quantum computation, I can toss out fancy technical terms in physics that wouldn't mean anything, but mostly it all revolves around the quality of mysteriousness. And primarily because these mysteries point to something beyond themselves. In other words, it's not just the simple fact of the mystery, but rather that the mystery evokes a sense of wonder about the worlds beyond, which I intuit are there.
The last question, Gilad. אנחנו צריכים לסיים בשתיים. I think it interests a lot of people here. What are the chances that the normal science, the regular science, will accept theories like Kabbalah or the way we present Kabbalah, Kabbalah as a science, or the science of Kabbalah, or the way of thinking of Baal HaSulam, etc.?
Okay, so here too there are two parts to the question. So, and let me address. Let me split off the two parts. First, what is the attitude towards science, and when will science in general accept that the mechanical view of science is not correct? So set aside Kabbalah, teachings of the Baal HaSulam, and so on. What happened over many, many centuries is that science originally had a more or less religious view of things and saw the world as animated with all kinds of forces. Spiritual, religious forces, demons, spirits, whatnot. And it was not really scientific. And then modern mechanical science came along and said, no, none of that is correct. The world really can be understood according to mechanical principles of physics and chemistry. And it's all purely mechanical. And there are no vital forces. There are no spirits and demons inhabiting matter and making it do what it does. Objects don't move because it's animated by a spirit. Objects move because of action and reaction. Chemical reactions don't happen according to alchemical spirits. They happen according to chemical reactions which can be quantified and governed mechanically by mathematics. And this represented a tremendous advance in our ability to understand how matter worked. And it led to many, many, many of the advances that we benefit from today. I mentioned that this morning, that essentially all of modern medicine is based on this mechanical view. Now, up till about the 1930s, biology still was dominated by the view that biological science was different, that living matter had to be understood as composed of, yes, chemicals, but these chemicals were informed by a vital essence, something other than just matter. But biological science did not actually make any major scientific advance to come up with modern genetic engineering, molecular biology, pharmacology, that is to say, all the advances of modern medicine, not even antibiotics. None of that would have been possible until it got rid of the notion of vital essence, fired all the professors who continued to believe in that, and adopted a purely mechanical view, basically saying that biological living systems were just more complicated machines. Now, all of that whole idea was all built on the idea that every science, chemistry, biology, zoology, anthropology, study of human beings, sociology, study of human systems, going from the smaller scale up to the larger scale, every single science was modeling itself on physics as the queen of the sciences, which had this completely mathematically describable mechanical view of things. To this day, that process of every science attempting to model itself on Newtonian physics is not complete yet. Okay? Within the universities of the world, the faculties of the universities of the world haven't finished the process of attempting to mimic 19th century physics. In the meantime, physics has abandoned the physics that they're attempting to model themselves on. Not even biology, which deals with very low level, very small objects, not even molecular biology, has yet caught up with the quantum revolution. Last year, 2 years ago, I gave a seminar at Tulane University to the Department of Biochemistry. Biochemistry deals with molecules just somewhat larger than organic chemistry. And the chairman of the department there didn't know that the process of protein folding required taking into account quantum effects to understand, and therefore could not be understood in classical mechanical terms. So it has not yet even happened that relatively basic sciences have yet come to grips with the implications of quantum mechanics. Physics itself, even in physics, as I said at the beginning, most physicists haven't yet grappled with the implications of what it means that events occur in the physical universe without being completely determined by prior events in the physical universe. It still is something utterly shocking to the scientific worldview. So there is a slow revolution occurring. There are an increasingly large number of physicists, biophysicists, biomolecular scientists who are beginning to understand the impact of quantum mechanics. There are people, for example, who now recognize that evolution has incorporated quantum effects in shaping organisms. But these are isolated individuals. As these individuals have come to terms with this, some of them have begun to realize that it has this profound implication that the mechanical worldview is dead, and that there is something else. People like that will